Good afternoon. My name is Joe Cercello. With NXP Semiconductors, and I'm here today to present the results of work that we have been doing on what we call software PPA metrics. I will be presenting measurements from 3 production software releases that are specifically looking at static code size comparisons between RISC-V and the ARM Cortex-M processor architectures as used in microcontroller applications. Okay. So in hardware design, the notion of power, performance, and area as key metrics in overall SoC optimizations is well known. But what we'd like to do today is to redefine the PPA metrics into a software context that can be used for MCU architectural analysis. In this context, the P is the relative power in terms of memory, both code and data access rates. The second P is a measure of performance in terms of execution cycles and instruction execution path length. And A is a proxy for area based on relative static code size. Further, the work that is presented today is limited to the study of the relative static code sizes. For constrained MCU compute environments, especially in IoT, edge processing, and other applications, key size is a key metric. Code size is a key metric. Non-volatile code memories like flash and ROM are typically relatively large physical blocks, and in addition, they typically represent a significant amount of the overall dynamic power dissipation. So this becomes a very key element in terms of optimizing for an MCU design. Let's look at the software packages that were used in this analysis. There were 3 specific packages that we used. 2 were production security releases, and 1 had to do with generic integer processing. In the security subsystems that NXP uses and includes in our devices, they oftentimes have processing elements in them. The original implementations in use today typically use ARM Cortex-M cores as the processing elements. For this work, we want to retarget those software bases to the RISC-V ISA for this study using the GCC compiler and the architectural definition of what's known as RV32IMC. So this is basically the standard RISC-V integer instruction set, add support for multiply and divide, as well as compressed opcodes. We're going to study and look at various compiler optimization levels from OS, which is a size optimization, all the way up to O3, which is for maximum performance. I should also mention that RISC-V has one architecture issue that's already been addressed by the compilers in terms of function entry and exit. So these are the so-called prologue and epilogue portions of a function where registers are being saved and then restored upon entry and then restored at exit time. There is a compiler option currently supported that's called Msave Restore that makes use of common shared routines to store integer registers away at entry and then restore them at exit. So the baseline integer architecture requires that all individual registers would be stored with individual instructions to save each register one at a time, and then the comparable load at exit time to reload the registers. This is a known weakness, if you will, in static code size, so that this particular compiler optimization exists where shared routines will be used to improve code density at the cost of a decrease in performance, slight decrease in performance. In terms of the software packages, the first package is from our IMX product family. This represents about 100,000 lines of source C code. And for this analysis, we will be looking at an ARM Cortex-M, that is the V7M architectural definition GCC versus the RISC-V GCC. The second package is a crypto library, or cryptolib as we know it. This is about 40K lines of source code. And here we'll actually be doing 2 separate comparisons. One, again, using GCC for Cortex-M4 versus RISC-V, but then also another comparison point using the ARM-C compiler, ARM-CC version 7M architecture versus RISC-V. The third software package is what we call the embedded Llvm proprietary programs. So these are customer provided benchmarks that we have collected over many years. Most of these represent critical performance kernels, although each is relatively small in size. If we look across the entire set of the 11 programs, it represents about 50K to 80K of text and read-only data sections as a function of the compiler optimization levels. They cover a variety of application areas. We'll get into a little more detail on that later on. It represents about 50K lines of source code. And for this work, we're going to use GCC 10.2.0 for the analysis, both for, again, Cortex M4 target as well as the RV32 IMC target for RISC-V. The results of this work are kind of initial out-of-the-box data, and there's certainly more analysis work that needs to be done on this particular set of benchmarks. Okay, let's review the results from software package number 1. Again, this was the IMX security production release. Basically, there's two different versions of this data, the chart on the left and the table on the right. It's the same data, just presented differently, either graphically or in tabular form. If we look up at the table here, what we can see is the rows here represent different optimization levels for the compiler. Also, each optimization level having either the Msave Restore optimization included or not. This first column here is the Cortex M4 GCC byte size. As you can see there, quite a range based on the optimization level. The next column over is the RV32 IMC results. Again, the byte size for those sections. This highlighted column here shows the relative size comparison. So this is the information we're really interested in, looking at RV32, the RISC-V size versus Cortex M4, and you can see that these results vary from 1.08 to about 1.15. This particular table also has these two additional columns where we look at the relative size of the compiler object file growth, looking at as a function of optimization using the OS, the size optimization as the reference point. So you can see by the time we get down to 03, it's almost 30% bigger than that size optimized version, both for Cortex M4 as well as RV32. So in terms of what we've got here, the smaller the number, the better that is. That's showing that the RISC-V code size growth is minimized relative to Cortex M4. And if we look across this range of 1.08 to 1.15x, that basically represents what we kind of had as an upper end of our expectations based on publicly available information. This is the same type of presentation on software package 2. Again, if we look at the tabular form, we've got the GCC results for Cortex M4 listed here. This analysis also looked at the ARM C compiler, and you can see the results from that. And then those are compared against the RV32 IMC GCC results, which are listed here. So this data for the RISC-V versus Cortex M4 GCC, you can see we're in the range of 1.29 to 1.32. If we look at RISC-V versus the Cortex M4 using the ARM C compiler, then the size difference goes up considerably, and we're talking about a range of 1.35 up to 1.52. And certainly the range, when you look across both of these, going from 1.29 up to 1.52, that was considerably beyond what we thought the upper end of expectations would lead us to believe on this work. So let's make some observations about this software package number 2. First of all, we wanted to try and assess what the root cause might have been for the expanded code size for RISC-V. So we looked at a number of attributes of this software package, and they're itemized here. So we had characteristics of very highly modular, relatively short functions. And of course, that is an opportunity to have exposure to the function prologue and epilogue differences amplified, if you will. There's a lot of indirect memory pointer references within data structures. The APIs that this crypto library uses have basically a fairly large number of parameters for most of the calls. There's also a relatively high data memory access rates per instruction in these functions. And finally, this code is all written using NXP's secure coding guidelines. And this is an interesting factor in this whole thing. We've not been able to establish whether there's anything specifically related to those guidelines that may be also factoring into the increased code size. So what we've done is gone through kind of a side-by-side analysis of two example functions, looking at basically the assembly compiler outputs kind of side by side. We have two functions here. One, function A is a very short function that has a very high relative code expansion, and function B is a longer function where the code expansion is a little less. So legal constraints do not allow us to show the actual emitted instructions from the compiler, but we've tried to summarize it this way, looking at breaking down the functions into prologue, epilogue, and basic blocks. And you can see we have essentially on the left side of this, we've got information for function A. Essentially, we've got the breakdown in rows of the different functions, and then we have a couple of columns here. First of all, this is showing the ARM compiler results for the V6M processor architecture. This was actually a Cortex M0 Plus design. So this basically says, okay, we had one instruction that was 16 bits long for the prologue, etc. And right across from that, kind of lined up side by side, we would have the RV32 IMC results from GCC, and you can see each function, the number of instructions and the bits associated with those static instructions for this particular function. So as I mentioned, this function A is very simple, but you can see the highlighted areas here in yellow where we've got some significant differences, and these are basically kind of summary metrics based on this. We've got the number of bits per instruction. Looking at the GCC, we see that there's a 1.3x growth of the number of relative bits per instruction. There's a 1.6x growth in the number of static instructions in the function, and you multiply those two and you get a 2.1x static code size expansion on that particular function. At the bottom here on both function A and function B, we've got some additional data on memory loads and stores, calls, and some conditional and unconditional branch statistics down there. If we look at function B, as I mentioned, this is a little bit longer. There's more stuff going on here. You can see that the differences between the ARM CC results and the GCC results are not nearly as dramatic as they were for function A, but nevertheless, when we multiply the increased relative bits per instruction and the number of relative instructions, we see a 1.4 essentially x static code size growth for this particular function. So if we look at this in a little bit more detail, just some additional points here, the RISC-V options did not include the Msave Restore compiler flag as we were trying to do this kind of side-by-side comparison. You do see the effects of the function prologue and epilogue are fairly obvious. And of course, recall that the ARM ISA supports load and store multiple register instructions. So a single instruction can save all the registers needed at function entry, and a single load multiple can restore them at exit. The number of instructions within the basic blocks, though, are fairly similar. So there was some tracking there, but the number of instruction bits per basic block were not. So that seems to suggest that there's non-optimal compressed instruction definitions and encodings, as well as non-optimal encodings for functional calls. The differences in the data memory accesses need additional study, but we believe that those need to be studied in the scope of much larger functions and not kind of micro focusing on these really tiny functions, but that's an area that needs more study. Within the RISC-V.org community, there is a relatively new code size task group that has been formed and is actively investigating into these topics. So we're certainly following the work that task group is doing, and hope that they can come up with some extensions to the ISA to improve overall density. I'm going to switch gears now and talk about NXP's LLVM RISC compiler. So we have been actively developing an internal RISC-V LLVM RISC compiler for about the last year and a half. This was originally based on LLVM 10.0 with frequent merges from the master. There are a number of specific areas that this compiler work is focused on, and I would propose that the first three of these that are listed here are the most important. So first of all, we're looking at code size optimizations for small footprint devices, as we've been talking about. LLVM supports an OZ option, which is OS plus the Msave Restore, as well as a number of other compiler attributes that try to minimize the overall code size. We've got enhancements that support NXP-specific hardware features, as well as some fairly advanced optimizations for many core architectures. And then you can see there's a number of other areas where we're adding support within LLVM. If we look at our standard comparison chart here, this was using a different version of software package number 2. This was targeting a specific product with its own unique requirements, and as a result, it had a different number of software components versus the previous software package number 2. So the work that was done here was we were looking at GCC OS, the size optimization with Msave Restore versus LLVM, looking at both OS and OZ for that. And again, in the familiar format we've got these results. So you can see that, again, using the GCC as the baseline, LLVM OS by itself was about 6% larger, and the OZ optimization level, which essentially is OS plus Msave Restore plus a bunch of other things, reduces the gap down to 3%. So I think we would say that we've basically been seeing fairly good progress from the LLVM compiler work in terms of reducing the static code size gap versus GCC. Okay, we now would like to turn our attention to software package number 3. And again, this 11 integer benchmarks that we've collected from customers, proprietary kernels of code that they've developed and shared with us over the years. So on the left-hand side of this chart, you can see a number of, basically a brief description of all the benchmarks here and what they cover. There are a number of automotive applications that are used, as well as one automotive application that had auto code generation, which is an interesting difference. For the non-automotive stuff, we've got a number of things covering communications, crypto, basic math, and filtering, as well as some disk controller optimization functions. So all of this data is summarized on the table on the right, again, in our kind of standardized format here. Each row here represents one of these embedded 11 benchmarks that we have. And we have the GCC size for Cortex M4 target, and then the RV32 IMC target also. So the two compiler optimizations we looked at here were OS and then O3. So we've got all the individual sizes here, and then the relative difference, again, looking at RISC-V versus Cortex M4. You can see across the OS optimizations, we had a 1.37 geometric mean across all of those. For the O3, it was a little bit lower, down to 1.34. So a couple of things to note here. Again, the relative geometric mean in this case across these benchmarks was much higher than we would have expected in terms of where public domain information suggests the relative code size would be at. The other thing to note was there was an awful lot of variability across these different benchmarks. So as I mentioned, this initial work was kind of a simple, straight out of the box compile, and there's obviously a whole lot more work that we need to do to analyze these data points. Okay, in terms of summary and next steps, so exactly what conclusions can we draw from this work to this point? So basically, we're seeing that at least on some of the workloads that we're measuring, we're seeing that the relative static code density for these production applications and customer kernels seem to be well beyond the advertised expectations. In terms of next step, I've already mentioned the RISC-V.org code size task group that's currently investigating ISA extensions to make improvements in this area. Within NXP, we want to do a more detailed analysis for this software package number 3, the embedded Llvm that I just was talking about. We'd also like to continue the static code analysis for other production code applications. Again, given that this is such a key parameter in many MCU configurations. We'd also like to go back and do some runtime analysis metric works on the 2 Ps, power and performance. So again, these map to memory access rates per instruction, looking at both instruction fetches as well as data loads and stores, as well as the dynamic stack memory footprint. And finally, I'd like to acknowledge a number of my colleagues, Antoine, who helped with software package number 1, Pim with software package number 2, John Russo did a lot of work on the Llvm and GCC 10.2.0, and then John Mitchell, who provided some support on the software number 3 package. So thanks to my colleagues for all of their help. So with that basically finishes my presentation. I want to thank you for your attendance, and can I answer any questions? Thank you.